Hi, welcome to the first video abstract from the SIM group. Today we're going to talk about our results on nanomanipulation of clusters on an insulating surface. We study the manipulation using atomic force microscopy tools, both theoretical and experimental. An atomic force microscope, AFM, works so that a very sharp tip, atomistically sharp even, is brought close to the surface being studied. When the tip is just a few angstroms away from the surface, it can feel a nanoscopic force, and an image of the surface can be obtained by scanning with the tip. You could say the AFM feels the surface to find what is there, but one can also use the tip to manipulate atoms or clusters on the surface. This kind of manipulation is interesting in of itself, and it can also be used for building structures for further studies of, for example, catalysis or nanoelectronics. Here we see a schematic representation of the system studied, gold on sodium chloride. As manipulation of clusters on such insulators is new, our study is also a proof of principle work. The cubes represent the common defects on the surface, sodium vacancies, missing sodium ions, at steps, and chlorine vacancies on the terrace. By simulating the system using quantum mechanical methods, we predicted that small gold clusters are mobile on the surface, but they will attach at the vacancies. Once anchored, the way the clusters prefer to move depends on how they bond with the surface, and this is determined by the type of vacancy they have paired with. Here we see the preferred pathways for a cluster at chlorine and sodium vacancies. We find especially that if a cluster is paired with a sodium vacancy, it bonds to the surface only at one of its edges. Here we see the electron glue, which attaches the cluster edge to a row of chlorine ions on the surface. In this kind of configuration, the cluster likes to slide only in the direction parallel to the bonded edge. Overall, the calculations predict that a gold cluster will move very differently depending on what is underneath it on the surface. On the perfect surface, gold is mobile, and on a sodium vacancy, it strongly prefers to move in the 110 surface direction. In the experiments, gold is deposited on the sodium chloride surface as atoms. The gold atoms diffuse around until they find vacancies, forming nucleation centers for the clusters. The common defect on the terrace is the chlorine vacancy, while at the steps, sodium vacancies are more commonly found. This means that clusters that grow in different places should also behave differently. To see if this is truly the case, we manipulated clusters in different ways, by scanning with the tip laterally and by pushing down vertically. Here we see a series of images taken between manipulation steps for a cluster found on a terrace. As expected, the cluster can be moved in any direction. When a cluster is picked from a step edge, the observed movement is very different. The cluster only moves in the 110 surface direction. This is in agreement with simulations of a gold cluster and a sodium vacancy. To summarize, both theory and experiments suggest that the manipulation characteristics of clusters are indeed governed by the defects they attach to. For manipulation purposes, knowing the types of defects allows you to control the movement of clusters. Vice versa, doing manipulation experiments could allow one to distinguish between different types of defect cluster complexes. The ability to create, characterize, and manipulate cluster defect complexes could be applied, for instance, in studies of catalysis, where the reactivity of such structures could be explored in different arrangements and surface sites.